Hello, everyone, and welcome online. My name is Benjamin de Bucher, and I'm the head of events content for JEC Group. Thank you for joining us today. Today's webinar is how to produce isotropic molds for composite material parts in less than a week. Yes, you heard it right, in less than a week. This webinar will introduce the award-winning Massivit 10,000 additive manufacturing system designed to automate and accelerate tooling for composite material parts by enabling direct casting of molds, jigs, fixtures, and mandrels. You will learn how to shorten tooling workflow from 19 steps down to only just 4, enabling the production of a mold in less than a week. A variety of custom tooling application will be explored for the marine, railway, automotive, construction, aerospace, home refurbishments, and sports industries. You will also get a sneak peek of the Massivit 10,000 before its official launch at JEC WORLD in May. But who is Massivit 3D? Massivit 3D is a leading provider of large-scale 3D printing systems based in Israel with an install base across 40 countries. We will be hearing first from Erez Zimmerman, the CEO of Massivit 3D. Erez has a vast experience in multidisciplinary additive manufacturing systems, as well as large format printing technologies. He holds a bachelor in electrical engineering and an MBA from Bar Ilan University in Israel. Prior to serving as both CEO and VP Global Sales at Massivit 3D, he held a number of executive positions at Matan Digital Printers, Object Geometries, and CTEX Vision in various business development, product management, marketing, and R&D roles. We will be also talking to Nir Dvir, Industrial Solutions Account Manager at Massivit 3D. Nir will do the live demo of the Massivit 10,000. Hello, Nir. Nir has over 20 years experience in the global manufacturing and printing area. He's a qualified printing engineer and has served in a range of product, technical, sales, and marketing roles at UPO, Daiso, and KA. Last but not least, we will be joined by Frank Glovax, Editor-in-Chief of JEC Composites magazine and Head of Technical Content at JEC Group. Frank will share his insight on the additive manufacturing industry and the technology developed by Massivit 3D. So let's now discover how to produce isotropic molds for composite material parts in less than a week. Erez, welcome online. It's a pleasure to have with us today. Could you please give us a little bit of background behind Massivit 3D?
Hello, Benjamin. Hello, Frank. First of all, I would like to thank you enabling Massivit to present in this webinar in JEC. I appreciate a lot this stage for us. Today, together with my colleague Nir Dvir, which is our Industrial Solution Manager, we will present how to produce isotropic molds for composite materials parts in less than 1 week. Our agenda for today is to have an overview of Massivit 3D, to explain in details how to overcome composite manufacturing bottlenecks, automating tools. We will show you how our cutting-edge technology, the Massivit 10,000, how it works. And of course, we will show you some applications, what our customers can do with our Massivit 10,000 technology. Nir, my colleague, will have a live demonstration. And of course, Frank will make a review on the market needs from his experience. Without further ado, allow me to start my presentation. Before we start, I would like to explain to you a little bit who we are, who is Massivit 3D. So Massivit 3D is founded in 2013, and we have a disruptive technology for additive manufacturing. Our technology, the main claim to fame is the ability to print 30 times faster and to produce mold than any other technology. Our technology, of course, is backed with 50 patents around the globe. We are a public company traded as of last year, and our proven technology is already have install base in different 40 countries around the globe with more than 164 units from our first generation technology. A little bit more about the company is to let you know that our key investors that invested in the company in the past, the first one is Stratasys, one of the leading vendors in 3D printing arena, and Yaskawa, which is the leading robotic arm, a Japanese company. Among them, we have financial investors that invest in the company. So that's really a run slide about us. And Massivit is founded in order to address a strong need where there is a need for large-scale parts in several industries, like automotive, like marine, like rail, aerospace, and others. And usually when we talk about 3D printing, most of the 3D printing are focusing on small scale, let's say the size of a shoebox, and Massivit actually developed a large-scale 3D printer that we can literally print a car bumper or a train parts in hours instead of weeks. Now, Benjamin, we're going to talk about today about composites manufacturing, and we're going to talk about overcoming the bottlenecks that we have in production line. Would you like to say a few words about the poll?
Yeah, exactly. It's time for the first poll of this webinar. So I'm going to publish it right now. And again, for the audience, I invite you to answer the poll in the poll section at the bottom right of your screen. So let's publish the poll. So the question is, how do you manufacture molds today? And you have four possible choice. The first one is being you manufacture molds through hand layup. The second one being through CNC machining. The third one being through additive manufacturing system. And the fourth choice is I don't manufacture molds. So please answer the questions. And so far, we have most of the audience manufacturing molds through CNC machining, around 40%, hand layup around 25%, 20% of the audience don't manufacture molds, and only 15% manufacture molds through additive manufacturing system. Thank you. Go on, Eras.
Thank you. This is interesting results, and I encourage everyone to participate. We're going to have additional polls during this webinar. I think it's important to have an interactive Zoom and not me presenting. So I appreciate everyone that taking answers to the poll. And this is interesting. 40% are doing with CNC, you mentioned, and 15% are doing it via 3D printing. This is exciting news to hear and to learn, because we develop a cutting edge technology that do 3D printing instead of using CNC machine. And I'm sure that all the audience that we have today know that the bottleneck in producing composite parts, whether it's carbon or fiberglass, is usually the mold. The mold usually takes time to produce it. It's slow, it's complicated, it's expensive process, it creates lots of waste. And I'm sure that you're all familiar with this process. So on the right-hand side, I'm sure that you're all familiar with production line, how it looks. And on the left side, you also know that these molds need to be stored. And you can see on the left side that these molds are being stored sometimes for years, because if you need another part, you need to manufacture it again, and the mold need to be taken care very cautiously. Now, imagine that conventional production mold, which usually start in CAD design, we have the mold production process that takes 19 steps, and it usually takes 5 to 8 weeks until you get the final mold, and from there you are producing an end part. Now let's continue our interactive survey here with the poll, and Benjamin, the stage is yours to the next poll.
Thank you very much, Ares. So I just published the second poll. The question is, how long does it take you to build a mold? So less than 2 weeks, 2 to 4 weeks, 5 to 8 weeks, or more than 8 weeks. So please vote. And so far, the audience, about 50% answer 2 to 4 weeks. Now it's 40%, 25%, 5 to 8 weeks, more than 8 weeks for almost 30% now, and less than 2 weeks, only 9%. So you should
Can you
rely
please
to
can you please repeat the results? I just
yeah,
want to.
so 42% it's 2 to 4 weeks,
Mhm, mhm.
25% is 5 to 8 weeks, 25% again more than 8 weeks, and only 8% less than 2 weeks.
So what is the average? Again, it's about, let's say, 6 weeks.
2 to 4 weeks, it's the main answer.
The main answer. So imagine that instead 4 weeks, you can do it only in 5 days. And instead of doing it in 19 steps, doing the male shape and so on and so forth, some people count it differently a little bit. But imagine that instead of doing it in 4 weeks, as the survey just showed, you can do it just in click of a button. And instead of doing it in weeks, you can do it in days. You're going to have the cut design, you're going to have Massivit solution, and then you have the mold that's being prepared. Now, as I mentioned, instead of 19 steps, you can do it in 4 steps only: to print the mold, to put it in an oven for curing, remove sacrificial pattern, polish it, whether it's done in CNC or manually, and then you have the final mold. Now, during my presentation, I will talk about our groundbreaking technology, and you will see in a minute a video that we prepared that demonstrate what are the 4 steps. Now, we are producing an automatic tooling for composite within days. I'm happy to hear in the previous poll that 15% of the people in this meeting today are using 3D printing to produce molds. And we develop a cutting edge technology, the Massivit 10,000, that can print directly isotropic molds. And we can do it 80 times faster than any other technology. And as a rule of thumb, we can print about 35 centimeter an hour in a z-axis. There is no need for plugs. You reduce the waste. We have an excellent CTE and IHDT, and the build volume is about 1.4 meter by 1.1 by 1.5 meter. Now, you will see in a minute how it works, and let's see this video that demonstrate, and later on you can also see with Nir how we are doing it in live demonstration. So let's see a quick video how technology is working, and I will explain in more details, of course.
The Massivit 10,000 automates tooling for composite manufacturing. This cutting-edge additive manufacturing system enables direct casting with high-performance materials to dramatically speed up tooling. Introducing the world's first isotropic 3D printed mold. The Massivit 10,000 empowers composite material manufacturers to produce custom molds, tools, mandrels, plugs, jigs, and fixtures within a matter of days instead of weeks. The Massivit 10,000 shortens your mold production workflow from 19 steps down to 4 simple steps and eliminates the need for a plug. So how does it work? The Massivit 10,000 utilizes a dual-head system to directly print and cast molds. Based on an initial CAD design, the first head 3D prints an outer sacrificial shell at high speed. The second head intermittently casts a thermoset material into that shell as it builds. The shell is comprised of 2 thin walls made of water-breakable photopolymer material that polymerizes instantly under ultraviolet light. The thermoset material forms a solid isotropic mold. The mold can then be post-cured in an oven to improve its mechanical properties at elevated temperatures. It is then simply immersed in a bath of plain water, causing the shell to crumble away. The Massivit 10,000 offers near-net shape casting. The mold can be post-finished as needed. Your high-temp, high-performance isotropic mold is now ready for use within less than a week. Benefit from advanced casting materials that ensure consistent mechanical and thermal properties across all axes. Discover digital tooling for a wide range of industries including maritime, automotive, rail, defense, aerospace, sporting goods, and home refurbishments. Join the digital revolution with the award-winning Massivit 10,000 additive tooling system, offering automated, high-speed tooling for composite manufacturing.
So indeed, as you see, we have a disruptive technology that we call cast in motion. And I will just emphasize again that we have one head in our printing system, which called Massivit 10,000, that print a sacrificial pattern. The sacrificial pattern is printed with water breakable material that can print complex shapes, high speed. There is no need for there is no waste creation, and the resolution is high, and of course this is accurate. So that's the first head. And then we have the casting head that actually come and print isotropic material with low CT and high HDT that actually can work in high performance, and this is a durable mold. And this creates an official digital tooling of molds. Now, the material that I'm sure that you're all interested, what are these materials? So the sacrificial shape or the envelope of the mold is made of ultra-fast sacrificial shell that made of water breakable material. There is no need for support structure. I see that some of the participants here are familiar with 3D printing. So there is no need for support structure. This is a very unique technology that we have. And then you dip the part in the water and it's unattended shell removal after several hours. Now, the cast in motion material, we're actually using an epoxy-based material that has chopped fibers inside and other fillers that brings the true isotropic mechanical properties. It has resistance to high temperature and it has low CT, as I mentioned. Now, this technology enable to reduce 80% in times, to reduce dramatically the cost of production of mold, and it's almost labor-free, enable people to do other tasks while they are utilizing our machine. Now, Benjamin, we have another poll here, and I'm interested to learn more what will be the next survey from our audience today.
Thank you, Erez. That's true. It's time for the last poll for this webinar. I'm just publishing the question. Have you ever considered producing mold using additive manufacturing? So the answer are simple, yes or no. Please answer the question. So yeah, most of the audience consider producing molds using additive manufacturing around 90%. So which is really good. Yeah, 92% consider producing molds using additive manufacturing.
Indeed, this is very encouraging news. I see that the people are open for new technology, and this is important because if people are 92% already engaged with 3D printing technology, they are aware of the pros and cons of 3D, and definitely Massivit, the fact that we are printing isotropic molds is a game changer in terms of mechanical property of the mold. Now, let's see what our customers can do and what are the applications that can be utilized and inject your imagination. So we can do molds, we can do plugs or masters, we can do mandrels, and we can do real prototyping for other applications. Let's see some of the examples. Here is the molds. Molds is very straightforward. Here you can see our car seat was 3D printed with the shell inside the machine. This is, you can see the proportions. We have the nice lady here that holds the chair. This is a car seat. And here you can see the final carbon fiber that being manufactured with these molds. So to give you some proportions of size, you can see it's about 90, almost 1 meter height, almost 80 centimeters width, and 67 centimeters width. And you can see that the printing time to produce such a mold will be 42 hours only. And this is why we say, as a rule of thumb, it takes at about 5 days to produce such industrial molds. Some of the molds will be much shorter than 5 days. Here we can see this is a hydrofoil skin for a flying catamaran. Here you can see the mold. Obviously, you understand that the shape, the geometry is like a half U shape. And to give you some ballpark figures, it's about 92 centimeters by 330 millimeters, and you can see that the print time is only 8 hours. And imagine that in CNC machine, you need to take a big bulk and do subtractive of lots of materials. And here you can print only the desired material in this hydrofoil skin. Another nice example, this is a radome for the defense industry. You can see this is like the dome in front of this vehicle. And you can see that to print, again, the proportion is about radius of 71 centimeters, and the z-axis is about 45 centimeters. And to print this radome mold will take about 11 hours only. Imagine how much waste you need to create when you produce this radome in CNC machines. Now, we have another interesting that we can do both tools and we can do also the jigs. Here you can see I'm holding a bike seat mold. Nir will show it as well. This is the final product, the bike seat. But this is the mold, as you've seen also in the video that we presented earlier. And if you look carefully, of course, we have the shape of the mold. And moreover, you can see here the jigs. It can be designed in your CAD. And also, if you look carefully, we have inserts over here. So this is all can be done in 3D printing. And again, you print only the desired material and you don't need to create waste. And this is a green solution. Mandrels. Mandrel is very challenging application. And I would like to ask and everyone to have a look on this duct. It's like an air vent. You look on the geometry, which is closed. It actually looks like a pipe with all kinds of shapes inside. And to produce this part, I'm sure that everyone that participates in this webinar today understand that this is a very complex geometry to create. Usually it may be needed for 2 molds in order to produce it. And you can see the seam or the parting line. And with Massivit, I just want to show you quickly the process. You just bring your CAD, you save it as STL. STL is the format of 3D printing. You drop it to our tray in our Massivit software. You print it as you've seen in the video. This is a water breakable. It printed only the water breakable shell. Then afterwards, you layouting around the printed core with one continuous piece of fabric, sponge it with epoxy, add it into a vacuum bag. Then in order to remove it, it's a one-time sacrificial tool. You're actually dipping it, as you see here, in a simple tap water. There is no chemical, very simple, very easy of use. The parts, the inner core crumbles into flakes, and it leaves the outside composite duct, as you can see here, as the final product. And again, to produce this part in CNC or alternative technology is 10 times more complicated, I would say. Now, plugs. Plug is also very important. I'm sure that you're all familiar. This is very simple to print. As you've seen in the video, you print the shell, cast inside our material, dip it in the water, the walls are falling apart, and then you can use, this is a plug. For some people call it master, some people call it a plug. And this is a part, by the way, of a bat for the marine industry. So again, all kinds of application can be utilizing with our machine. This machine can also use for prototyping. You can print all kinds of parts. This is, here you can see the back area of the marine of the yacht was 3D printed, reinforced with fiberglass directly on our material, sand and polish, and you can see the final part. You can see this is a train that the front bumper was 3D printed with Massivit. And of course, it can be used for other molding applications like thermoforming, utilizing the Massivit 10,000 technology. I'm sure that you're all veteran and familiar with the composite industry, and we are applying to the aerospace, the defense, the marine, construction, sports and good, automotive, and renewable energies. These are all the use cases and others for composite material. Now, this is all excellent in our presentation, but I think it's very important now to let Nir to do a live demonstration from our production line downstairs.
So Erez sent a lot of information over, and I want to make it real, to show you the technology and to try and show you a live demo of the Massivit 10,000. We are standing here in Israel at the headquarters, standing in front of the machine. You can see the volume of the machine. Again, we talk about a print volume of 1.1 by 1.4 and 1.5 meter height. The key for us is the fast printing. And how do we do it? First of all, we use our core technology and using our dispenser. As you can see here, the dispenser dispenses material, push material through a tip that determines the resolution that we can apply. Okay, we have different resolution. On top of the head, you will see that we bring a UV ring. The UV ring that you can see here will cure the layer immediately. Okay, the UV ring will cure the layer immediately. It means that if I have layers, I can print layers on top of each other, and in the same way I can print layers next to each other. It means that if I can print layers next to each other, I don't need any infill or support material. For example, just to present something that just we are printing in minutes, this is a hollow object. I'll try to show it to the camera. Yeah, okay. It is a hollow object, and that was printed in this way. One layer on top of each other and one layer next to each other in that way. And by that, I'm saving a lot of material, a lot of cost, a lot of time to remove the infill or support. And this is our GDP technology where all is based on. Now, adding into that, going into the Massivit 10,000, as presented by Erez, we want to show the cast-in-motion technology. For the cast-in-motion technology, we are using two printing heads. The first head will do the shell, as you can see here, the white area, and the gray area is the casted material. Here we talk about epoxy, low CTE, temperature up to 155 degrees Celsius. Okay, once my geometry is printed, I will cure it, I will soak it in water, it will fall apart, the layer will fall apart, and I will remain with the mold. This is my mold. This is what I will remain with. Okay, and as you can see, the surface still need a touch, a small touch. And after the finishing process, I will get a very smooth surface with just a little bit of machining, milling, or sanding, depends on the quality that you want to reach. Again, you as the end customer, of course, would like to generate carbon parts with the molds that we are preparing in days instead of weeks. Erez was talking about creating mold, creating masters, and also mandrels. I want to show the mandrel. If you have a carbon piece that has an undercut and you want to create it, you need a special mold. Not anymore in this size. You can print a mandrel. As you can see here, this is the mandrel of that part. It's a one-timer mold. Okay, you can print the mandrel, put the carbon fiber on top of it, cure it, and dip it in water, and you have your carbon piece, not within weeks, within days. Okay, so this is also important. Okay, I want to show the mold here. Okay, I don't have a master here, but I will show a mold here. What I want to show, important to say that when you are, it is after a milling, of course, and scanning, and important to say that when we create digitally the mold, we already take into consideration the jigs and fixtures. So you save also a lot of time by creating the form that you need for optimal heating properties and optimal handling properties if you need to carry it from one side to each other. Okay. What we see here, this is the Massivit 10,000 that will go to the JEC World now in May. It is ready to be shipped. So what we will do for you, we are going to move to one of our production line, machine of our production line that is producing today, and show you the cast in motion live in just a few seconds. Okay, I hope that you can come closer to the camera, to the front. Okay, I hope it is visible enough.
Yes, Neil, we can see the printing process. Neil, we can see the UV print.
So what you can see here, you can see the GDP head that is printing, and it will print this sandwich layer that we talked before. And depends on the exothermic that I want to reach at the Massivit. I will actually print a few layers together and then cast the epoxy. Okay, Kim, I know it is complicated. You can also show it here on the screen. Okay, so the operator, you can see two cameras. The first camera is the camera of the GDP. The head it's printing with the curing in a record speed, and on the right side we will see the casting head that will cast every few moments. From my side, this is most of. Maybe we will show also the casting system that is coming. Next to the Massivit 10,000, we have a mixing unit. Okay, this is the Massivit CMS. Here we are mixing epoxy, part A and part B. Important to say that, as you know, epoxy will start the reaction immediately as the two parts will come together. And this is happening only during the casting process, just at the head. So the casting system will allow us the right temperature, the right viscosity, just having everything ready for the casting process in the machine. What I suggest that till we get to see the casting process, maybe in 3 or 4 minutes, we will take a few questions with Frank, and try during the question also to see the casting process.
Okay, thank you, Nir. Personally, I have to say that I think that your solution answers some of the needs that are not fully met with other technologies yet. In our industry, all starts with a mold. A good mold is the key of a good part. It's absolutely mandatory. If you not able to manufacture something properly as a mold, no point to make composites. So molds are usually costly and take a lot of time to manufacture, as you said. So the drawbacks are in manual making. It's really time consuming. Traditional epoxy tooling boards require a lot of milling, and molds that are made by a fuse modeling deposition, another additive manufacturing method, often implies anisotropy. In addition, nowadays, fast and bespoke solutions are required in many applications. So plus, we need to reduce waste of materials. And I think your solution overcome most of these problems. And yes, it is a new solution. Okay, for plugs, you have some rivals, but for mold making, fast mold making, I think you have a really good niche in terms of process to allow people to manufacture molds really effectively. So I will try to gather my questions together with the ones we already had. Please feel free to ask us questions in the right side of your screen in the questions tab. How many parts can you produce with one mold?
We are targeting, we are designing our material, our epoxy, in terms of design and strength, to withstand the low hundreds of parts. Of course, it has to do with geometry. But maybe with that said, I will say that, you know, that when you make molds, sometimes they might be damaged during your production. And it is very, very easy to repair them. Frank, with the same material that we are printing, we can just repair them.
My second question would be about the finishing of the mold. You already answered partially, but I'm really curious about the roughness of the mold just right after the removal of the outer shell. So you said you need milling, sanding, but do you also need any sealing or coating of the mold?
First of all, the resolution of the mold is determined by the operator. We have a different resolution, and it has to do with your workflow. If you want to invest more in the milling process, or you want to invest more in the digital process. For example, if I will print with our highest resolution, 0.5 millimeter, I will need just a little bit of a milling. About the coating, release liner and stuff like this, I believe that whoever make parts out of mold can answer that better than me. But yes, a little bit milling. If you're using a higher or lower resolution, you might need a little bit of milling. But think about it, that we are printing only what we need. We are not coming out of a block. So if we have hollow geometries, we are not printing the hollow geometries and just printing the walls of the mold.
Thank you for your answer. And on most additive manufacturing technologies, you get different distortion towards any direction, X, Y, and Z, especially the Z-axis with fuse deposition modeling, for example. And how do you handle that with Massivit 10,000?
Good question. Yes, we have the isotropic behavior. We are actually casting one layer on top of each other of epoxy. We are the lower layer is still in a green status, that the upper layer get connected, and actually they even mix together. And by that, it's not layers that are connected, but one unit. And by that, it's one block. And,
yes.
And by that, we are creating the same distortion or similarity between X, Y, and Z itself.
Yes, you're still in the takt time of the resin, so you can, it's, let's say, like a continuous resin one.
Exactly. Right? Are we casting now? Soon. We are casting soon in 1 minute? About a minute and a half.
Or maybe just one quick question before the demonstration. So, what is the process for creating jigs and fixture with for the 3D printing molds? Do you add some inserts, for example, or?
I think that one of the biggest advantage in digital printing is the ability to design everything to fit your insert, and to design the jigs and fixtures. We still have a lot to learn, but yes, we already present, as I presented before in the mold, we are already printing the mold with the tools to hold it. Okay, so also here we are saving a lot of time. Okay,
Thank you, Nia. Maybe time for the demonstration, and
yeah.
we will have some other questions from the audience.
Kim, maybe it is easier to show it on the screen, you know, Kim. Okay. 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 Great. We can have another answer till we get the casting process in action.
Okay, so we have a question about the resin you can cast with the casting head. Someone is asking if you can cast thermoplastic resins. I have a really big doubt about that. It's your take, so.
Wow, it's a tough question. We prove in the lab that we can cast a lot of material. Today, the idea is, Kim, maybe you can show just shortly the mixer that we are using. We are using I would say a relatively simple mixer with a big hole. This will allow us to use different material. This is how we design our different epoxy systems, and I believe that this technology will enable us to print also other materials. I cannot confirm thermoplastic at the moment, but we know there is some need. At the end, our first technology has 5 different solutions, and they are based on customers' demand. If the demand will be, we want to have it. What you can see now that the printing head moved aside, and you can see the casting head, actually the epoxy that just was waiting at the entry of the machine to be mixed live and casted, one layer on top of each other. And as you remember, the lower layer is still in green status, and they are mixed together. The volume that we are casting is very big, so the casting process is relatively short, and the GDP head will go immediately into action and print the next layers. I hope that the casting process came through. Thank you, Kim. Do we have more questions, Frank?
Yes, before leaving the audience question, I have one. What about the availability of your solutions? Where can you send the Massivit 10,000? Have you got, for example, representative in France?
First of all, about the availability of the Massivit 10,000, we are in a beta stage where we have already our first beta, and going to have soon more availability from the second part of the year after the beta testing. About sales, service, support, Massivit America, Massivit Europe, and Massivit in Asia has its own infrastructure. Specifically in Europe, our demo center in Massivit Europe is located in Belgium. And specifically, if you ask about France, in France also we have service engineers.
Okay, so a global footprint, which is good to sell this kind of equipment.
If you have 160 or more than 150 units around the world in 40 countries around the globe, you do need a good infrastructure and stable system.
Thank you, Nia. We have some other question if we have time. Benjamin?
Yes, of course. Thank you very much, Frank, for this, and thanks, Nia, for the live demo. We have very positive feedback in the chat about the demo. The audience enjoyed it a lot. So let's now open the floor to question. We have already have a few in the question tab. Thank you very much for this. Let's take the first questions from Emil Edlund, who is asking what geometrical tolerances are possible to attain directly from the print process before reductive processes if needed.
Okay, about the tolerance and accuracy, it is a good question. First of all, in terms of the machine, it is designed to be, as we say, up to 4 times more accurate than our GDP system. Our GDP system is plus minus one millimeter on a meter. But here we talk about creating molds mainly, and if we understand that the last stage is a minimal milling process, I believe that the customer would choose to print in a lower resolution and do the milling at the end rather than printing slower and having more accurate. So it is lower than 1 millimeter on a meter. And we will have to understand if we want to invest in more accurate system or to adjust it into the process of the customer.
Thank you, Nir. Let's move to the next question from Sibel Yildiz, who is asking, is it possible to repair the mold?
Yes, we repair molds here. We are using part A and B materials, and the same way that the machine is mixing those parts, we can offline mix them and repair molds. This is one of the advantage of the system. Okay, the ability to repair molds.
Thank you. Next question from Ahmet Abdullah Goksen. Does dispensing head need to be changed after every print, or is there a cleaning system on printer? If so, is it air purge or solvent purge?
First of all, there are different systems. If we talk about during the printing, we have automatic system that AI connected to AI that will clean the head in case the head is getting dirty. It is getting cleaned automatically, and if needed, there is also a cleaning system at the machine, and it will be sent automatically to be cleaned. This is concerning the tip. Every shift or every night, you will clean it and you can reuse it. About the head, we claim that this head can withstand many hours. If we talk about 1,000 or customers of us are using those heads longer than a year. And if not, you can refurbish the head with us or buy new ones. They are not a consumable such as our printing material. You can use them again and again and again.
Thank you, Nir. Next question from Quentin Gauvignon, who is asking, can you add short reinforced carbon fiber in the isotropic resin to reduce CTE of the mold?
I forgot the name, but he's already telling everyone what we did. In order to come to low CTE, we do add some chopped fibers, and this will allow us to come to the lower CTE than aluminum. Okay, so yes, we are already using chopped fibers in our solution, in our epoxy solution. He is right, or she, I'm sorry.
He is.
He, I'm sorry.
No problem. So the next question was, is the CTE comparable to aluminum tools? Is it higher or lower? So you just answered it.
Yes.
Saying it's
we are targeting lower CTE than aluminum with the target to make bigger molds than aluminum. We know that after half a meter, most of the market will move out of aluminum.
Thank you. Next question from Peter Bernhofer asking, taking the feet shell as an example, is it possible to produce more than 100 pieces?
Yes, yes, yes. We haven't come to the limit of manufacturing, but the specific mold is a very easy mold to release the part from. So we believe that it will stand more, of course, more than 100 times. Again, it is not designed for thousands of times, okay? But more than 100, it should be done easily, for sure, with this geometry.
Thank you again, Nir. Next question from Quentin again, Quentin Gonvignon. What are the stiffness and strengths of your isotropic resin?
Hi, and let me take this question.
Yes.
We have a clear data sheet. You know, when you look on mechanical properties of any material, there's a clear data sheet, and we highlighted several of the things that on the data sheet, which is the HDT of 155 Celsius degrees. There is CTE, there is textile strength, and others materials. You can send us an email, and of course, or seeing it on our website, you can see the full technical data sheet of our printed mold material. I see Nir is back.
Am I back?
Yes,
Yes,
you
you're there, Nir.
Okay.
Yes.
That's good. I don't know
I
why I'm
took the
disappearing.
question, Nir.
Thank you very much, Erez. I needed the help here.
So let's move to the next one from Marcel Brijne, who is saying this is a very nice technique. Could you give us a few words or your thoughts on how your technique compares to the print tech from AirTech Advanced Material Group? Thank you in advance.
Okay, I'm not claiming to be the expert in AirTech, but if I'm not mistaken, we talk about FDM. FDM solution need to melt kind of plastic, is it a wire or parts, and then cool them down. They need to be melted one on top of each other, and actually can never be isotropic. Our solution, the way we cast the material, we are generating isotropic solution, which is very, very important at the end when you are producing parts in a high temperature. For jigs and fixtures, we understand that FDM is very good. But again, if you are referring to FDM, the major advantage is our capability to generate isotropic solution, while FDM need to be very careful when they put one layer on top of each other, and now they connect it in order to get a good bond between the layers.
Thank you, Nir. Next question from Zaim Refai, who is asking how the inserts are placed in the mold. Is it automated?
It is not automated. I understand what insert is talking about. We talk about those inserts. The reason that we use inserts has to do with the orientation of our solution, this is our orientation compared to the CNC solution, milling solution. And what we want to achieve, quick mount to the CNC. The inserts are part of our table, and we can take the decision where we are printing in order to get the optimal adjustment for the milling process.
Thank you. A question from Hartmut Wolf, who is asking what to do with the water after dissolving the outer material.
Mm-hmm. So the water can be, this is a simple plain tap water. And after the part was dissolved, you can just put the water in a drain, simple drain. There is no need for special treatment. And if you look carefully, there is the shell that fall apart. This is actually can be reused as a plastic material. And you just separate it in between. It just can be filtered, and this is very simple.
Another question from Abhidip Kumar, who is saying he must say that it's a brilliant technology, so congratulations.
Thank you so much. Thank you so much for a compliment.
Next question from Abhidip Kumar, who is asking, how did you conceive the shell casting concept?
How did we
conceive? Like,
you mean how did we invent it?
Yeah, exactly.
Yes,
how do you
I mean, I think I didn't mention. Yes, I think I didn't mention it at the beginning of our meeting today, but the founder of Massivit 3D, his name is Gershon Miller, and he's actually the founder of object geometry today. It's called Stratasys. And he's more than 30 years in the 3D printing industry, and he actually is a very visionary person. And this is one of the things that he said, this is something that we can do. We can print supportless, and then we can cast inside. And based on his vast experience, we developed this technology.
Thank you, Erez. Rajendra Walalkar is asking if you have a presence in India.
We have a presence in India. We have a salesperson. His name is Ashan. You can drop me an email or to our info, and we'll be happy to refer you to them.
Thank you again, Erez. And
we don't have in Madagascar, I have to say. Okay? but India is relatively important for us, and that's why we have a sales representative there.
Pedro Alzoriz is asking, how do you create the print programs?
Usually people design in CAD. It can be SolidWorks, CATIA, Pro Engineer. We take the CAD file, or it actually save as in the CAD file as STL. STL is the common format for 3D printing. STL is acronym for Standard Triangular Language. You can save it in any CAD file, an STL, send it to our, we call it Massivit Smart Station. It actually takes the file and slice it into layers, and it knows to calculate what should be the layer thickness, when it should be casted. So we take it from the CAD, we have our Massivit Smart in the way, and that actually works with the printer. So every CAD software that is available in the market, we can accept the files from them.
Thanks, Erez. And let's move to the last question we received from Josh Webb. Will you eventually integrate composites fibers in your mixture for even stronger end-of-use parts?
First of all, as you see the technology, the cast in motion, you had a sneak preview today, is definitely, from the questions that I see from the audience today, is scalable. The first material that we released was called CIM 155. It's epoxy-based material that includes all kinds of fillers, like carbon fiber and other fillers that are available in the market. In the future, we will definitely release additional materials that are already in our R&D laboratory, and some of them can be used for all kinds of applications. Some of them can be for end-use parts, but definitely we will release additional materials in the future, and this platform will be able to accept additional materials.
Thank you very much, Erez. We have now come to the end of this event. I want to thank everyone for joining us.
If I may say,
yes,
if I may say one last slide, thank you. I would like, first of all, to thank JEC Composites, to Frank and to Benjamin for this stage. I've seen that there was lots of engagement with the audience today. So if you have any additional questions, feel free to send us email to our info, and you can send us some files to do some benchmarking and evaluate and feel a little bit about our technology. And of course, I invite everyone for our official introduction in JEC WORLD in May 3rd this year. It's behind the corner. Actually, it's really behind the corner. So we will have the machine there with the molds that we show you, and you can touch the molds and can touch the technology. Can meet Nir and myself, and you are all invited to meet us there. And again, I would like to thank Benjamin and Frank for this stage today.
Thank you very
Thank you,
much,
Erez.
Erez. Thank you again, Erez, Nir, all people involved at Massivit 3D for this webinar, as well as Frank for his participation today. Thank you. The webinar was recorded and the link will be sent to you immediately now, together with the link to download Erez's presentation. And it will be available soon also, the video on JEC Group Web TV on jccomposites.tv, where you can access to all previous webinars, exclusive video contents, and conferences of JEC Group events. So we hope to welcome you online soon, and I wish you a very good day. Bye-bye, and thank you, everybody.
Thank you. Bye-bye.
Thank you.
Thank you. Thank you all. Bye-bye.